All right, there we go. Hello, everyone. Welcome back to another week of Data 8. Today, we're going to be talking about hypothesis testing. I have a lot of announcements today, so listen up. Homework 4 is due tomorrow at midnight, so make sure you have homework 4 turned in. Homework 5 will be due Friday of the midterm, but you should try to get it done before the midterm because it'll help you if you do it before the midterm rather than after the midterm. So homework 5 we'll try to release it earlier if possible, but at latest it'll be released tomorrow. Try to do it before the midterm so you can get the practice that you need. Okay. Lab this Wednesday and Thursday will be midterm review. So TAs, during the lab, you'll be working with your TAs on some problems from past midterms and working on those together. You can ask questions. You can just use that time to help you study. Oh, I forgot to mention that there's a midterm on Friday. So there is a midterm on Friday, 10 to 12 p.m. It will be held at normal class time. We're trying to reserve different rooms for the midterm so that you have better tables and the lighting will be a little bit brighter. I'll get back to you on that and where you'll go for the midterm, but otherwise it will be held here in class 10 to 12. Okay. If you are a DSP student, I will email you. Okay, so if I do not email you by tonight, please send me an email saying that, hello, I'm a DSP student, you missed me. Okay, so I'll email you by tonight. Midterm does count as attending lecture. So that means that you get 2 hours of lecture attendance for coming to the midterm because you guys will all be here. However, I would recommend coming to lecture because the lecture content until Wednesday will be covered on the midterm. And it is quite tricky. So I hope that you guys, if you don't come to lecture, at least spend time reviewing the material and really trying to understand it before the midterm. Okay. I mentioned that lecture content up to Wednesday will be on the midterm, and that's because lecture on Thursday will be midterm review. So during class on Thursday, I'm going to do some review of concepts, practice problems, all that stuff. Try to help you guys out. Okay. Office hours on Thursday and Friday have been moved to 367 Cori instead of the normal 258 Cori. So on office hours on Thursday, Friday, 367 Cori, not 258. Finally, I was asked a little while ago about whether or not employment or being employed could count as an excuse for lecture attendance. We have decided that that is OK. So if you can show me proof of employment and the times that you are employed or required to come into work, that would count as being excused from lecture attendance. Okay. Finally, I want to draw your attention once again to the feedback form that is on Data 8's website. So here we go, make that bigger. And if you click here, go to links, there is a feedback form. Okay, so again, if you have anything you want me to know, so this will only be viewed by me. If there's anything you want me to know or want to say about how the course is treating you or how you're feeling about it or any positive or negative experiences at all, please feel free to fill out that feedback form. And I promise I'll look through every single one. I just want to make sure that's there. I show that. Okay, close that. Back to slides. And I believe that is all the announcements I got. Any questions about that list of 10 announcements? All right, so I have not had the time to put the announcements on the website, but I will do so today. So remind me if I don't put it up on the website by today. You don't have to write down and remember all 10 of those things. So everyone, applaud yourself for finishing project 1. Woohoo! Good job, everyone. Okay. So as you guys know, or if you did project 1, hopefully, you will know that in the project 1, we asked you to do a lot of manipulation with tables, right? You did grouping a lot, you did joining a lot, selecting, using where, a ton, right? And I want to just say that the point of project 1 was not to blast you with table questions and manipulation questions. It was kind of that in order to get you feeling comfortable with using table methods. But the real kind of overarching reason that we created project 1 in the first place was to show you that with some basic tools, we've only been in this class for what, 3 weeks now? With some basic tools or 3 weeks of class, you can already do some pretty sophisticated analysis, right? Taking some basic tools, piecing them together, you can ask some pretty interesting questions. And actually, in project 1, we looked at global trends, right? Global trends in poverty, global trends in mortality, all that kind of stuff. Pretty interesting, and we can do that with just a little bit of data analysis tools. Okay. in particular, I want to show you gapminder.org, which is the website where all the data in Project 1 came from. It's all available there. You can browse it at your own leisure. And right here, they have all the plots that you made in Project 1. So you didn't actually have to do Project 1 to do them, but now you know how to make the plots. So good on you. Okay. I'll just show you. Oh, darn. Come on. Well, this one. OK. So for example, we can look at using the tools that they have on Gapminder. We can plot child mortality rate versus babies per woman. Here's 1960. Here is China. Here is India. Let's try to find the US. The US is down here, right? So low, relatively low child mortality, relatively low babies per woman, 1960. And we can show, we'll press that button and watch what happens to the countries as time goes on, right? So what do you notice? Countries move from like here in general, like down to here, right? So if I scroll back, you can watch them go backwards in time from the top right corner down to the bottom left corner. So what does that say? That says that in general, it looks like most of these countries here had a high mortality rate. So this is like 320 deaths per 1,000 births, which is like extremely high, right? That's like 1/3 of babies dying. And here we have babies per woman, so that's really high. And it shows that as time goes on, both the child mortality rate and the babies per woman go down. And the reason why I want to show you that is because there was a point in time where people were concerned about the overpopulation of the Earth, right? They were like, okay, if we reach above like some certain number of people, everything's gonna go down the drain because we won't have enough resources. We're gonna have global warming, like just the Earth will go down in flames, right? And they were like, and there was an argument for a time that said, okay, we shouldn't really worry about child mortality rate because if more babies die, less people will be on the Earth, right? So it's kind of like oh, okay, fine. You know, you can kind of see the logic in that argument somewhat, although it makes it really uncomfortable to admit it. And other people were like, no, we should just save all the babies because that's the right thing to do. And it turns out that you can have the best of both worlds. In this case, we found out using data that if you lower child mortality rate and like provide health services to countries, people will have less babies because they won't like think, oh, I need 8 babies because only like 3 of them will live, right? So it turns out that using data, we can kind of make arguments or make decisions. It's probably the only way that we are able to really make a clear call on what kind of policy to enact, especially with regard to something as what is this? Contentious or controversial, as controversial as this, right? I want to show you one more. So here we have life expectancy versus the income per person. So here we have, why can't I click find? Nope. Okay. Darn it. What about that? Okay. So here we have life expectancy in years, and here's income per person. This is on a logarithmic scale here, so every like marker is kind of like an exponential increase. So here we have the United States at like 20K per person. Down here we have China, which only is every person is making about like only $1,000, right? So here, not that much money, lots of money. Life expectancy is low, life expectancy is high, right? So here's the US. I can click that. And here's China, I can click that. And we can see what happens to both of them over time. So here we go. Very cool. Okay, so we see for the US that the US got both richer and people live longer. So it kind of went up in like the slowly sloping line right there, slowly sloping path. But China, on the other hand, kind of took this like first they had higher life expectancy and then people made money. And if you look at the groups of countries, so let me scroll back. So here is 1960. Okay. And if you take a look at these countries, how do I remove this? I'm puzzling. Okay, deselect. There we go. So a lot of the countries in this region right here, you'll notice if you look at this plot, a large majority of them went up in life expectancy first and then started making more money. And that can kind of show you that all these countries, once they implemented basic health services and like had hospitals and all that stuff, then people started making money because they lived longer to make money. So stuff like that you can discover just by looking at the data. I hope you guys can check it out on your own time and give you inspiration for more data analysis. Woohoo, data. All right. So let me start off with where we left off on Friday. Okay, so we're looking on Friday jury panels. In particular, I had this slide where I said there are some eligible jurors in a county, and then the county selects a list of eligible residents. Okay, so to actually be eligible to be put on a jury, you need to speak English, be a resident of that county, not have a felony, different criteria that they use. Okay, so here's a list of eligible people that they can put on a jury. And then from those eligible people, they supposedly are supposed to select at random people to put on a jury panel. Okay, so eligible residents, select at random a jury panel, and then they form the final jury from that jury panel. In California, there's a particular law that says we need to select at random a group that represents a cross-section of the population served by the court. Okay, so that's kind of the goal. The goal is to create panels that are representative of the people of that county. Okay, and we saw that in the case of Swain versus Alabama, it was a little suspect, right? Because the population was about 26% black, and the panel that Swain actually had in his court case was only 8% black, 8 out of 100 people. Okay, and we looked at that and we were like, is that actual jury panel likely? And we can use the methods that we learned in class to kind of figure out whether that actual panel of 8 black people was likely to occur if we had drawn at random from the population of all eligible jurors. So what I'm going to do now is run a bunch of code. And what I'm going to emphasize to you is don't worry too much about the actual code in these boxes, because I'm just going to run through them. Okay? I need you to focus right now on the high-level idea of what we're trying to do. We start off with the distributions of eligible jurors in the actual panel. There we go. Make that bigger. Okay. So we have eligible jurors and we have the actual panel. Okay. Eligible jurors, 26% black. Then we're going to draw panels at random from the population. Okay. So draw a panel of 100, see what it looks like. Draw another panel of 100, see what it looks like. And then from there, we can see whether the actual panel was likely to occur if we had drawn at random from the population, right? Because if we draw panels at random from the population and none of them have like 8 or less blacks in them, then we can say, oh, okay, my actual panel was pretty unlikely to occur by chance. Okay, so let's take a look at that. So here's step 1, the distributions of population and sample. Not too bad. And then we did this method yesterday, or not yesterday, on Friday, where we can call this function, which gives us a new table with another random sample. Okay, so here I'm drawing a random sample from the population. In this particular random panel, 22 were black, 78 were not black. Okay. Finally, we can run that a bunch of times and see whether our panel was unlikely. And I talked briefly about this idea of total variation distance, which is just a measure of how different two distributions are. Okay, so that means the higher the TVD, the more different. The lower the TVD, the more similar. For now, that's all I really need to care about. Okay, so we have this TVD function. If we call it on the original table, what we find is a TVD between the eligible jurors and our panel was 0.18. Okay, so keep that in your mind. 0.18 was our original TVD. What we want to do is when we draw panels at random, find a TVD for each random panel. So draw 1,000 panels of 100 people each, find the TVDs of each one between the sampled panel and the actual population. So we see that we get a bunch of TVDs here, and we can draw a histogram. Okay, so here I have a histogram. What is this showing me? This is showing me what TVDs are likely to occur if I draw at random, right? So every single bar contains a number of random panels that I drew from the population. And the TVD is here. So this is basically saying most random panels should have a TVD of between 0 and 0.1, right? So between 0 and 0.1 is the most likely TVD to occur if I draw at random from a population. If I look down here, okay, fine. Maybe I got 0.125 if I'm really unlucky. But beyond like 0.15, there is like no panels down here, right? And if you look at our original TVD, it was 0.18, which is all the way over here, right? Like all the way down here. And so we can say, I left you with a cliffhanger last Friday, but now we look at this again and we can say, well, if I draw at random, my TVDs basically all end up in this range right here. That means that my original panel TVD is really high, like way higher than what I would expect if I drew a random from population. And so I can say, well, it seems very unlikely that my actual panel was drawn at random from my eligible jurors. So that's the conclusion we can make by looking at this data set. Any questions about that? OK, so unfortunately for Mr. Swain, the Supreme Court, so he had a hearing in Alabama, and then he went to the Supreme Court because his lawyers said, oh, this panel seems unfair. And unfortunately, in 1962, the Supreme Court ruled that the panel was actually OK. They were like, well, there's not that much difference between the panel and what was actually there in the population, which was kind of suspicious. And it turns out that in the 1980s, some parts of that ruling were overturned, and they changed the laws a little bit to try to make it more fair. So that was in 1962. That's the unfortunate reality of what happened. But what about nowadays? Okay, so in 2010, the ACLU, the American Civil Liberties Union, I believe, released a report, Ethnic Disparities in Alameda County, which happens to be the county that Berkeley is a part of. Okay, so our county, they looked at the ethnic distributions here, and they're looking at our juries. Okay, so looking at basically the juries that come out of Berkeley, Alameda, that area. Okay, so here's what they found. They found that in our population in 2010, this was the distribution of ethnicities. Okay, so here we go. And what they did was they looked at 11 panels of felony trials in 2009 and 2010. 11 trials, looked at 11 panels. And they interviewed each panelist individually and took note of the ethnicity of each panelist. Okay, so each possible juror that will eventually become part of the jury. And this is a distribution that they found for those panels. Okay, so here's a table. I can also draw a bar chart. So let me draw a bar chart. Here is blue, dark blue is eligible, and yellow is the actual panel. Okay. So you can kind of see here some differences, right? So it looks like there are more Asians, less blacks, less Latinos, about the same number of whites, and more others in the actual panels than there were in what was eligible. And we can ask the same question of Alameda County today as we did of Swain in 1962, which is, were these panels likely to be drawn at random from the population? It's not exactly the same as asking whether the panels were fair, right? There's some slight differences there. People might not show up to court. There's some slight differences in kind of that number, but we can still ask the more precise question, the more narrow question of, were these panels likely to have been drawn from random from the population? Okay, so I can run through more or less the exact same steps and show you how we can do that analysis. All right, so we did step one, which is start with the distribution of the population as sample. So pretty simple. Now I want to draw panels at random from the population. Okay, so how do I do that? Start with my panels table. And I can see here I have these ethnicities. And I want to draw panels at random. Now the panels in this case, so the panel size of like this column right here altogether was about 1,400 people, because it had 11 trials. Okay, so 11 trials. Each trial had about a panel size of about 150. Okay, so a bunch of people here in these panels. And what I want to do is draw panels at random for my population. Okay, so what I can do is start with my panels and take the first and select out the first column. So select out ethnicity. Right. But I have here the five groupings of ethnicities. And as we discussed before, we can use .sample to sample at random with replacement from this group. Right? So if I sample and take a sample of size 100, now I have a list of 100 ethnicities drawn at random from the 5 possible original ethnicities. Right? So here I have a quote-unquote panel of 100 people drawn at random. However, the problem with drawing at random like this is that it draws uniformly at random, which means that each ethnicity is equally likely to appear. So if I actually take a panel of, let's say, like 10,000, and then group them together by the ethnicity, you'll see that each ethnicity appears about the same number of times, which is not actually drawing representative. It's not actually like representing the population. what we actually want to do is adjust the number of times, just the likelihood of each ethnicity appearing, so that a panel will reflect drawing at random from the population. Okay, so the way we do that is by taking this column here and saying, don't draw each ethnicity at 20%, like equally likely each one. Draw Asians at 15% likelihood, blacks at 18%, whites at 54%. Okay, so I'm going to take my panels and take the eligible column eligible. I have some proportions. The proportions here need to sum to 1, right? Because these are all like part of one population. And what I can do is, instead of sampling like this, all I need to do is say, don't sample uniformly at random, sample according to these weights. So I'm just saying, use these weights to sample instead of sampling out uniformly. And when I run this again, you'll see that I get about the correct proportion of each ethnicity. Now, it turns out that when you group, it'll sort this ethnicity column. So you see this other here has only 100, and the other actually occurred last in my original table. So it's kind of the grouping that makes the ordering appear differently. But you will notice that the proportions of each ethnicity are correct, right? So whites have about 5,400 in 10,000, and that was the proportion that I wanted. Okay, so that's how I can do that. And so what I can do there is now I have a panel of 10,000 people, but really I wanted a panel of 1,453 because I wanted to draw out another panel the same size as my original. So I'm going to put in my panel size. Okay, so now I have a panel of 1,453 potential jurors. And I can just convert those to proportions and then put them back in the original table as a column here, and I can now compare. Okay, so that will require me a couple more steps, but there's an easier way. I'm about to show you the easier way. So you don't actually have to do any of this. I want to show you this so you can know how to do it manually. But in reality, you probably want to use this function called proportions from distribution. Okay, so this magical function. Here's the documentation. As usual, question mark will bring this up, blah, 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 blah. I'll just show you how to use it. Okay, so the first argument is to pass in the table. By the way, a pro tip is if you're calling a function and you want to remember like which order the arguments come in and what arguments go in what position, you can press Shift Tab. So here I'm pressing Shift Tab, and this little box appears that shows me what exactly goes in the function. It's pretty handy. If I press Shift Tab more times, then the box becomes bigger. Okay. So very convenient. That's what I'm using right now. So the table goes first, panels. The label of my proportions goes second. So in this case, eligible. And finally, the last item there is my sample size, which was my panel size. Okay. And if I do that, then you'll see, aha, it draws a random sample and then takes the proportions and then puts them back in the original table for me. Saves me a bunch of typing, very convenient. Now these are in decimals. That's because by default, decimals will be displayed as decimals. I can change that by calling this sample 1, and then setting the format to be the same thing as what I did above. So if I just take that, calling .set format on a table doesn't change what's in the table. It just makes the table display differently. Yeah, Kevin?
What is the third argument again in proportions from distribution? Third argument.
The third argument is the size of my sample. Okay, so in this case, I'm drawing a sample of size 1,453, and then saying, OK, now draw the sample, find the proportions of each category, put those back in my original table. So now I can compare, this was my population. This is my actual panel. These are my actual panels. Here is a random sample for my population. Okay, so here I've drawn one sample at random, and I can compare it. I can just draw a bar chart. Okay, so a bar chart. Here we go. So you can see that the random sample looks pretty much like the population, right? So this bar went up a little bit, but otherwise pretty close. This bar went up a little bit as well, but otherwise pretty close. This bar went down a little bit, right? Because as a random process, I could get a little bit more or a little bit less of each category. In fact, it's technically possible that I get all 1,453 people were, say, whites, right? I could possibly get that bar to be just all the way up and everything else be at 0. It's a possibility, right? Because I'm drawing at random. It turns out that most of the time you get something that looks like the actual population. Okay, so here's a random sample, a random panel, comparing it with my population, comparing it with my actual panel, the yellow. Any questions about that? Okay. So let me make a brief step back to my slides. And talk about, remind you guys again what we talked about when we talked about empirical distributions, right? So if you remember, last week we talked about two different types of distributions. We talked about a probability distribution and an empirical distribution. Okay, so I used the example of rolling a die. And what we said was, okay, roll a die. If I roll a die 6,000 times, I should see 1,000 of those, about 1,000 of those rolls be heads. I mean, not heads, be sixes, right? Be a 6. And it turns out that in the case of a die, what we said was each face is equally likely to occur. So the probability of each face is 1/6, right? And we said that is the probability distribution because that is the precise mathematical probability that each face occurs. Okay, that is a probability distribution. And then we said, okay, an empirical distribution is, let's say I just roll the die. Okay, so I take the die, roll it 6,000 times, and then I can count out the number of times each 6 appears, and say, okay, based on that, I can make an estimate for how likely the 6 is going to show up on my die roll. Okay, so in this case, I'm going to use some terminology here. So in this case, we're talking about distribution of a statistic. In this particular example, when I roll a 6 on a die, that's the and I rolled a die 10,000 times, or let's say 6,000 times because it's divisible by 6. I roll a die 6,000 times. My statistic in that case is the number of 6s. Okay? It's just a quantity for a particular sample. My sample in this case is 1,000 die rolls. Okay? So sample is 1,000 die rolls. Statistic is number of 6s. My distribution is the chance of each outcome. Now, it's a little bit different than the chance of getting each roll, right? So the chance of getting each face on a die is 1/6. But now I'm asking the question, what is the chance of getting some number of 6s in 6,000 rolls, right? So I roll a die 6,000 times. I could get 0 6s. Right? It's a possibility. I could just get everything else. I could get 0 6s. I could also get 6,000 6s, right? Like every single roll could be a 6. That is also a possibility. So the probability of that happening is not 0. It's actually a little bit bigger than 0, but almost 0, right? But it's not 0. So in between 0 and 6,000, there's some number of 6s that could show up, right? I could get 2,000 6s. I could get 100 6s. Each of those outcomes of sampling has a chance, has a distribution. If I calculate that chance precisely using the laws of probability, what we have is what's called a sampling distribution, right? So that is, for a particular sample, what is the probability of getting the result of my statistic, right? So if I roll a die 6,000 times, what is the probability of getting 1,000 6s? What is the probability of getting 2,000 6s or 0 6s? That is my sampling distribution, the precise mathematical distribution. I can also find, this is also known as a probability distribution of the statistic, just like how we had probability distributions before, okay? An empirical distribution, on the other hand, is we just roll a die 6,000 times and count up how many 6s appear. If we do that a bunch of times, what we can then say is, okay, if I roll a die 6,000 times, it looks like 1,000 6s is pretty likely, like that happens pretty often. But I could also get 999 6s. I can get 1,001 6s. Those are like a little bit less likely, but still pretty likely. And as I go away from that, I kind of just see by rolling a die millions and billions of times that I can, as I roll my die and get more samples, I can approximate, I can get closer to my sampling distribution using the law of large numbers. Okay, so my empirical distribution in this case is my observations and my statistic. Okay, so there's a couple of different distributions here that I need you to kind of get clear in your head. Okay, one is the probability distribution of each face of the die, right? Each face of the die has 1/6 chance of appearing. That's the probability distribution of one roll. I'm talking now about the probability distribution of a statistic, which is what is the chance of a given number of 6s appearing in 6,000 rolls, right? So I'm saying I roll a die 6,000 times. what is a probability of 0 sixes, of 1 6, of 2 sixes, right? So it's a little bit different than just a probability distribution of the faces. Okay, so those are two separate distributions I need you to keep clear in your mind. Both of those probability distributions, both of those exact mathematical distributions can be approximated by using sampling, right? So roll my die, see how likely each face is to occur. That's approximating the first case, the probability distribution of my faces. In the second case, I roll my die 6,000 times, count the number of sixes, roll my die another 6,000 times, count the number of sixes, roll my die another 6,000 times, count the number of sixes, and that is my empirical distribution of my statistic, which is number of sixes in 6,000 rolls. It's a lot of sixes. Okay, so those things you really need to keep clear in your head, because we'll be approximating both of those, and you need to figure out and keep clear like which distribution am I actually trying to sample, which distribution am I actually trying to figure out in this case. Okay? Yeah, question?
Is it kind of like the probability distribution is more of like the theoretical one, and then empirical distribution is more like what we're testing?
That's right. That's right. So probability distribution we'll always refer to in this class, we'll always refer to the precise mathematical probability. Okay? The empirical distribution will always refer to when we sample and take samples, we can figure out, okay, it looks like in 100 samples, 100 dice rolls, like 1/6 of those, about 1/6 of those were sixes. So that's my approximation for the actual theoretical probability. Okay. Did you have a question, Kevin?
Is there a way to calculate the sampling distribution? Is there a way to like calculate it precisely?
So in some cases, yes. So in the case of the dice rolls, you can actually calculate precisely the chance that you get 1,000 sixes in 6,000 rolls using the laws of probability. We won't go over those in detail in this class because we'll just be using the empirical distribution. We find usually in a lot of cases, and especially when the cases are more complicated. So I'm going to go back to Alameda County jury panels. Okay, in that particular case, it's pretty hard. It's pretty hard to figure out the actual precise probability distribution, but it's usually possible. It might just require a lot of math. A lot of times it's easier just to take samples and see what happens. That's what we'll be using in this class from now on, basically. Okay. All right, so in Alameda County, our statistic was the total variation distance between a sample and the population distribution. Our distribution is a chance of each possible total variation distance. The sampling distribution is the exact probability of each TVD. Okay, so now we're kind of like going back to Alameda with the TVDs and all of that business. What I'm essentially saying here is it's possible to draw a panel that looks exactly like the population, right? If I draw a panel that looks exactly like my population, which could just happen by random chance, then my TVD will be 0 because that is exactly the same distribution as the population. On the other hand, it's possible to draw a distribution that's exactly different from my original population, which in that case, the TVD will be 1, right? So those two things are both possible. And I want to see what the distribution is between those two like possible values. Sampling distribution is the exact probability on a probability distribution. So sampling, probability distribution, those vocab terms are interchangeable. The empirical distribution is simulating panels and looking at the TVD distribution. Okay, so what I'm going to do now is look at that empirical distribution. Any questions? All right, so I'm going to do this, and I'm going to take attendance. Okay, so here we go, back to my notebook. So here I have one sample. I can find whether that TVD was likely. Okay, so I still have this table TVD method, which will calculate the TVD between two columns in a table. So I have table TVD of sample 1. I can find a TVD between eligible and the random sample. Eligible and the random sample. And I find that in my random sample, my TVD was 0.013, so pretty small. Okay. Let's do that a bunch of times. Okay, so I'm going to take this code here, which gets a new sample. I'm going to take this code here, which calculates the TVD. I'm just going to run it a bunch of times. For I in np.arange, let's say 1,000 repetitions. So repetitions equals 1,000 repetitions. Put that in a for loop, run that a bunch of times. I'm going to call this sample instead of sample 1. And I need to keep track of this TBD as always. So I'm going to call this my TBDs equals make array. I'm keep track of that TBD by appending to it. Append TBDs, put that in there. Now I have my TBDs. Okay. See that? I drew 1,000 panels. Took the TBD of each panel with the population. I'm going to put that into a table. Column. Let's call it TBD between population and random sample, and put in my TBDs in there. And now I have my results table. So I got that. Okay. So just a list of all my TBDs, or table of all my TBDs, sorry. And I can plot them on a histogram. Look at the distribution. Okay, so I have that. I'm going to change my bins a little bit. So I have that. Bins equals, I'm going to say a range, let's say goes from 0 to 0.2, incrementing by increments of 100th. There we go. Okay, so we have this distribution. This is the empirical distribution of my TBDs, right? Okay, so keep that clear. I drew panels at random, took the TBD of each panel with the population, and I put them on a histogram. We can look at the distribution and see which TBDs are likely or less likely to occur. So let's look at our original TBD. So I have this to kind of illustrate what's going on. So this function right here just says, OK, draw 1 sample, draw 10 samples, draw 20 samples. So what I can do here is say, OK, let's take 1 sample. As I increase the number of samples, my histogram will change, right? So I'm drawing more samples. As I draw more samples, my histogram looks more and more like the actual probability distribution of my statistics. So I'm going to draw more samples, blah, blah, blah. And I can see the bars here changing heights. And then finally, I go up to 1,000, or I guess 991. Oops, should be 1,000. And I can see here, here's my original histogram. Okay, so showing you the process of drawing samples, calculating the TBD, figuring out which TBDs are likely or less likely to occur. Okay, so I have that. That's weird. Okay, so let's look at our original TBD. So we have our original panels. You find the TBD between the eligible and the actual panels. See that? And I find that my original TBD was 0.14. If I look on my distribution of possible TBDs, it looks like that TBD is like way out here, right? Which means that it seems very unlikely that these panels were drawn at random from the population of eligible jurors. Right, so here I have 0.14 is my actual TBD. Here's my distribution of drawing panels at random from the population. Yeah.
If the TBD was really after at like 0.14, then how would you calculate it? Like, how would you calculate like the area of the histogram? Like, would it just be 0 or what?
Yeah. So Kevin's asking, how do we actually find the area like at this point, 0.14? We'll talk about that actually. We're going to get into it. That's actually a definition of p-value in hypothesis testing, but that's a sneak preview of what's coming next. Okay, so draw random, look at my TBD, 0.14 is all the way out here. Seems unlikely that it was drawn at random from the population. Then we can go back and say, OK, seems unlikely. Was there more stuff going on there that I should know about, right? So this is enough to give you suspicion, but it's not enough to say definitively that my panels were unfair. You just have to go back to the data and figure out all that stuff. But this right here, if we keep with our initial assumptions that our population looks like, let me just put panels here. If our population looks like this, and we assume that we selected at random a panel from our population, this panel is very unlikely to occur by chance. Okay. Any questions about that? It concerns me that you have no questions. Maybe you will soon. I'm going to take attendance first, so let's do that. Darn it. OK. And go for it. Oh, new features I'll love. I do want to learn more. Wow. Oh, sorry. The link was bit.ly/@-da. I got distracted by cool new features. So make sure to fill it out. After you're done filling it out, let me ask you a question. So in this case, we drew panels of size 1453 from our population. Okay, so we drew panels of size 1453, calculated the TBD of each panel, and then plotted them. What happens if our jury panels only had 50 people instead of 1543? Our panel size was, original panel size was 1453. What would change? What do you think would change if our panels only had 50 people instead of this number? What if our panel size was only 50? Okay. This question is pretty tricky. Talk it over for a good minute or two with your neighbor. Give it some thought. If you can understand this question and how it relates back to what we did before, I would say you have a pretty good idea of what this is all about. Okay, so think about this. I'll give you guys like 3 minutes to think about it. Okay, 50 people instead of 1453. What do you think would happen? How would our analysis change? Go.
Wait, so the panel size, like the total population of eligible juries, or what would they choose?
So Kevin asked, what does this number mean? This means that we had a population of possible ethnicities that we drew for a jury panel. In our original case, our combined panel size was 1453. So we drew 1453 people supposedly at random from the population. What would happen if our panel was only 50, size 50? Okay, think about it.
50 people is a much smaller sample size, so it deviates so much from the eligible, or it deviates that much from it. Well, it's a small sample size, so I guess our analysis would be a little bit different. We wouldn't consider it eligible. If we were 50,000, then well, it's more possible for us to get that. What we have in the panels, it's more likely with only 50 people. I think there's that calculation of like the area of the histogram where it's like you do the TBD divided by the sample size. If you divide it by 50, you get a much larger area of the histogram. So it's much more likely, you're much less likely to say like that was not a random sample, right? But if you divide that TBD by like 10,000 or 1,453, that would be a much smaller value. Potentially, because it's like 0. Definitely say, yeah, it was not the random. It was not the random.
All right, so got a couple minutes left, so I'm going to cut you a little short. Let's just see what happens. Okay, so I'm just going to take this, take my for loop, up here, down here, and change my panel size to 50. Okay, so my panel size is now 50. I run this again. Here are my new results. Okay, let me call this results 50, so I can show you the old results and the new results. I'm going to run, make sure my panel size here is back to 1543 or 1453, right? 1453. Go run that. Now I'm going to go down here. Now my panel size is 50. Results 50. Okay, so I have here a new table with new TBDs. Let's see what happens. Draw that. Here, my very first sample, my TBD is out here. I take 10 more samples. Now I'm more distributed across these TBDs. Take more samples, take more samples. And what do you notice? So here's my new one. Here is my old one, results.hist. Okay. So let me put back the bins the way they were before. Okay, so results.hist. Okay, so do that. Here is my old original sample size. Here's my new sample size. I'm going to increase n all the way back up to like 1,000. What do you notice between the two? This one is flatter, right? And also shorter. It's shorter because it's more distributed across different TBDs. But why? Why is it more distributed? It's because as your sample size gets smaller, it's more likely that you get a sample that looks pretty different from your population, right? So if my sample is only size 50, I can get some pretty big deviations from my population in just that sample of size 50. Once my sample size increases to 1453, then it's more and more likely that my sample will look like my population and my TBD will be lower, right? If my samples look more like my population, lower TBD. My samples look less than my population, higher TBD. In this case, I lowered my sample size, which means that it's more likely to get samples that look different, panels that look different than my population distribution. And that means that my TBDs are larger. And finally, if I look at my TBD now, so my original TBD was what, 0.14. If I had gotten an original TBD of 0.14 with a panel size of 50, that is suddenly no longer that different from what I would expect to be drawn at random. Okay, I see a lot of confused faces, but you have to kind of think about this some more. Okay, so spend some time tonight and tomorrow and next couple of days. Think about this quite deeply. Okay, so spend some time. Why? Why is it that when I change the sample size, my TBD gets larger, get a different distribution, get a completely different conclusion, actually. Get a different conclusion if my panel size was smaller. Okay, so think about it. So I mentioned before that I get this result. It seems like 0.14 is really unlikely. So we can look back at our data. So it turns out that when the ACLU released the report, they were using census data from 2000. And they released a report in 2010, which is when another census came out. But they're writing the report, so when they released it, they weren't able to use new data. So what I did is I went back to the census for 2010 and looked at the distributions of ethnicities in Alameda. So here are kind of the distributions now. Here we go. Okay. So we have here whites at 42%, African Americans at 12%. Okay. And if we look at our original table, we can see that the populations here have changed a little bit. So now it's 26% Asian, apparently. Wow, it's a lot more Asians. Whereas in 2000, it was 15%. 18% blacks versus 12%, like 13%. So all of our analysis for the past hour or so has been based on this assumption that our population looks like this, right? If our population doesn't look like what we claim it looks like, that also changes our analysis, okay? So I'll leave it as an exercise for you to see whether it's actually where that panel of 1453 actually looked like it was drawn from the population given this new data, okay? So what we've done, more or less, is what we call in statistics hypothesis testing. Close attendance. Wave your hand at me if you're still taking attendance. Okay, closing it. Okay. The basic idea is, so I'm going to give you very high-level steps today, and just tie it back to what we've done in class. Tomorrow we're going to talk in depth as to like nitty-gritty details of each particular step. Okay, but today I'm just going to give you high-level details. In hypothesis testing, my question is basically like, as oftentimes, does my sample look like my population? Does my jury look like it was drawn from a population? That is oftentimes a question in a hypothesis test. Okay. So in a hypothesis test, our first step, so this is like the formal steps that we do, not the steps that I've done in class, but the formal, like what you should do when running a hypothesis test. When you're trying to decide whether my juries were fair or not, whether my coin is unfair, whether, any questions like that is state my two hypotheses. Okay, so my null hypothesis says I drew my panel at random from the population, or my coin was fair to begin with, or like basically the status quo. Okay, the alternative says my results, which was that my jury panels, my jury panels look different from my actual population. The alternative says that was not due to random chance, that was due to some other factor that we haven't considered. Okay, so the null is very precise, saying my sample was from a population, nothing special happened there. My alternative says that's not the case. So my two kind of scenarios that I'm trying to decide between. My second step is to choose my test statistic, or the measure of difference between the sample. Okay? In the case of Alameda, we chose a TVD, because the TVD says my sample is similar, it's low. My samples are different, it's high. That's basically the only criteria we want when talking about test statistics. Okay? So choosing a value or a statistic about each sample that we can compute for random samples and for our original sample. Finally, we draw at random and look at that distribution of my statistic. In this case, in the past case, we're looking at the distribution of TVDs. Okay? Look at the distribution of TVDs and say, OK, is my actual result likely to happen? And we can approximate that by drawing at random, by computing an empirical distribution instead of the actual sampling distribution, which may or may not be easy to compute. Okay. So again, to recap, in the Alameda County, what we were trying to decide was, is my jury panel fair? Or more precisely, is my jury panel drawn at random from my population? So my null hypothesis is this. I'm running out of time, so I'm going to click through the slides here. You can read it on your own. Here we go. Okay. But those are my 3 steps for Alameda County. I had a little activity, but we'll do it tomorrow. I'll see you tomorrow.